Hey guys, Miss Marusik here, and in this video, I'm going to be reviewing common charges of ions, as well as looking at naming and formula writing for compounds. So to start us off here, I have a periodic table that I've done some labeling on. I've given myself the division line between metals and nonmetals, which is obviously important when you're talking about identifying a compound as being ionic or covalent. And then what I've done is on all my individual groups, I've gone in and put the most common ionic charge of that particular group. So for example here, our group 1 is +1, our group 2 is +2, and our group 13 is +3. On that metal side, we see those positive charges for those cations. When I get over here to the non-metals, I see those negative charges of -4, -3, -2, and -1 to show that the electrons are being gained over there. Notice also I don't have any charge with my noble gases because those have full valence S and P subshells, and so we don't need those to be included. Also, I want to point out that I put the positive or negative sign in front of the number, whereas some books and some teachers will put it at the end of the number. So don't get freaked out if you see it one way or the other. It really doesn't make a difference on how you're showing that. It's just kind of a personal preference. I like putting it at the beginning because then it looks kind of like how math does. However, you do notice that in here with the metals, I've kind of done a little bit of some weirdness here with a few things. First off, I have this zinc, cadmium, and silver little pattern here. These are our 3 transition metals that actually do have a set charge. All the rest of the transition metals have all kinds of various charges they could be. And so I would need more information to know exactly which charge that I had. And we're going to talk more about that here in a little bit. So I call this little pattern the silver staircase pattern. I remember that it starts with silver, so the silver staircase is silver at +1, zinc and cadmium at +2, and then group 13 at +3. That's the way I remember it. Also over here for group 14 metals, the big 2 that we see are tin and lead. They can be +2 or +4. Antimony and bismuth here in group 15 can be +3 or +5, depending on if they're losing just the P electrons or if they're losing the valence S and P electrons. For those of you that remember some stuff about electron configuration, we're going to re-go over that here in a couple weeks, but I just thought I'd kind of bring it back up because that's kind of the reason for some of those charges. However, you notice one of the other things that I did on this table is I highlighted some of these elements. Like I've highlighted all the transition elements with the exception of zinc, cadmium, and silver. And then I also highlighted those sections underneath group 14 and group 15 where we transition over to the metals. The reason why is that these are all metals that have more than one possible charge. And if I have a metal that has more than one possible charge, and what that means is that when I name the ionic compound, I must include a Roman numeral. I want somebody to be able to read my name that I wrote and be able to get back to the formula. And the only way to do that is if they know the charge that was being used on that element. So we have to make sure that we're communicating that information. It's probably the biggest mistake I see people make when they are writing names of formulas is they forget to put the Roman numeral. I'm sure some of you are thinking, yeah, I totally did that in pre-AP. I totally forgot Roman numerals all the time. So these are your sections that would need those Roman numerals, okay? Also down here, I kind of put a little refresher of how do we tell if a compound is ionic or covalent. Ionic compounds have a metal and a non-metal together, which is why we need to, recognize the difference between those. But we could also replace one or both of those pieces with a polyion. Now, I will tell you this, the only polyatomic ion that will replace the metal is ammonium, NH4 +1. And the reason why is because it's a cation, has a positive charge just like the other metals do. So a positive ion has to replace a positive ion, a negative ion would have to replace a negative ion kind of deal, okay? So covalent would be 2 nonmetals together. Now, the reason why we want to kind of recognize the difference there is because we approach both of those compounds very differently when we name and write the formulas. For ionic compounds, we use charges to figure out what our subscripts are. We want to make sure that the positives and negative are canceling out, and so that would determine what we're using for those subscripts. With a covalent, I don't care anything about charges. All I care about is what prefixes are there. Here, we're going to be sharing electrons, and so they're not really fully donating electrons in the same way that ionics are. We don't have full-blown ions with charges here. So keep in mind, you're not going to have to worry about balancing out the positive and negative, which is nice. I love writing the formulas and naming the formulas of covalents because they're so easy. Like there's so much less to worry about with those. Okay. Now on the next page of this, I have put kind of a, I don't know what you want to call it, like a blitz summary sheet of all things naming and formula writing. So if you are kind of forgetting some of the things that you learned in pre-P, this might be kind of a good place to start to kind of scan through. So I put kind of some tips if you're going from a name to a formula, or if you're going from a formula to a name, so you can kind of read through. But also down here, I put a refresher about acid naming and formula writing, because I feel like that was another area that was kind of tricky for some students. As well as I put a section about naming and writing formulas for hydrocarbons. I know not all schools do hydrocarbon naming and formula writing at the pre-P level. My school does, but I will show you how to do those so that way you could feel confident if you saw any of those kinds of examples. So what I'm going to do is I'm going to just kind of roll through some practice with y'all so that way we can kind of start to see and kind of refresh our memory if we, kind of make sure we know how to do this. Okay. I'm twisting my words here. So first thing I would do whenever I see any kind of compound is I want to go identify it as being ionic, covalent, or an acid. I feel like that is the most important first step you can take anytime you're doing these particular types of problems. So honestly, if I had a big old worksheet of naming and formula writing, I'm going to go identify them as ionic, acid, or covalent first before I do anything else to them. And I usually use like little symbols and stuff to help me. So first off, aluminum, I know that that is on that metal side of the zigzag, okay? And then I see oxide. Now, anytime I see IDE endings, with the exception of hydroxide and cyanide, any other time I see an IDE ending, I know I have a nonmetal. Okay, hydroxide and cyanide are exceptions because those are our two polyatomic ions that do have an IDE ending. So we kind of have to watch out for those. But once I see I don't have one of those, then I know I have a nonmetal. Well, metal plus a nonmetal, I know that that is ionic. Okay, so that means when I write the formula for this, I want to be concerned about charge. Okay, I want to make sure that my charges cancel out. Well, I see here that aluminum is in group 13, so that's going to have a positive 3 charge. And I see that oxygen is over here in group 16 nonmetal, so that would have a negative 2 charge. Well, to make those cancel out, I'm going to need 2 of that positive 3 thing, and I'm going to need 3 of that negative 2 thing, because that way when I add those up, a positive 3 times 2 is positive 6, a negative 2 times 3 would be a negative 6, a positive 6 and negative 6 would cancel out to 0. Again, the goal is you're trying to make your charges cancel out with ionics. So what that means is that I would need Al, 2 of them, and oxygen, 3 of those. So I would have Al2O3. All right, our next one here, iron 3 permanganate. So first off, iron is Fe. By the way, have we figured out yet? We're like, oh yeah, I need to know my element symbols here. This is the periodic table, by the way, that AP gives you. You notice there are no names on it. You got to know your names. Okay, so if you feel like you're kind of rusty on that, you might want to go back and refresh some of them. So iron is Fe. A funny way to remember that is female, like males and females. Female is Iron Man. Isn't that funny? I don't know why I find that one funny. Okay, maybe that's just me. I think that one's hilarious. So Fe is iron, so that's a metal. Okay, permanganate, I see that has an 8 endings to it. 8 endings indicate polyions as well as ite endings. So if I have a metal and a polyion, I know that this is also ionic, which means I need to be worried about charges. Now, iron is in that transition metal section. And you're like, well, how do I know what charge to use? Well, that's why they gave us this lovely Roman numeral here. The biggest mistake I see people make with Roman numerals when they see them is they think, oh, that means I have 3 irons. No, it does not mean you have 3 irons. What it means is that that iron has a charge of positive 3. Permanganate is MnO4 with a negative 1. So to balance out the positive 3 and the negative 1, I would need 3 of the permanganate polyions to balance out that positive 3. So when I write my compound here, that means I'm going to have Fe and just one of those. And then for that MnO4, I need 3 of those. And to show that, I can't just put a 3 over here because I need to show that I need 3 of that whole thing. So that means I would need those parentheses around it. Okay. Now, the next one is a little bit interesting. I notice it has 3 parts to its name. And anytime you see you have 3 parts to the name, there is a chance that part of that name has hydrate with it, which, oh wait, I see that here, octahydrate. What that means is that on the end of this, you are going to have some waters. And specifically, octa means we're going to have 8 waters. So I'm going to actually ignore that part for just a minute and just deal with barium hydroxide, okay? Barium is Ba. That is a metal that's in group 2, so that means that would have a positive 2 charge. Now, upon first glance, you're like, okay, wait a minute. Hydroxide, that's a polyion because hydroxide and cyanide are my 2 polyions that have an "ide" ending. So this is not just a normal nonmetal here, but rather polyion. And again, hydroxide is OH -1. Okay, so I'm going to need 2 of those hydroxides to cancel out the barium. So that means I'm going to have BaOH2. By the way, big mistake I see people make all the time. They write this and think that that's okay. Be careful there because that 2 is only applying to the H and not applying to the oxygen. So that is bad. You want to make sure you're applying that 2 to the whole entire polyatomic ion. Now, to address the octahydrate, what you do is you put a dot and then you put 8 H2O. That shows that there's 8 waters that are trapped within the crystal structure of the ionic compound. Okay, so now the next one. I see something kind of interesting about the next one off the bat. I'm like, whoa, tetraphosphorus hexaoxide. I am seeing some mega prefixes here. I see tetra, I see hexa, and I see a nonmetal, phosphorus, and an IDE nonmetal, because that's not hydroxide or cyanide. And so I know that this is covalent. Now, as soon as I see it's covalent, then I'm like, oh yeah, because that means I don't have to balance out charge. All I have to do is say, hey, phosphorus, it has tetra with it. That means I have 4 of those. Oxide, that has 6 with that. So that means I have O6 and I'm done. We love covalents. They're super crazy, insanely easy. Yay. Now, obviously these next 2 are both acids. Hello, they like literally have acid in the name. And whenever I see I have acid in the name, that means I know I'm going to have some ion that has hydrogens at the front of it. And the number of hydrogens comes from what we need to use to balance out the charge of whatever ion it's with. So like if my ion had a charge of -2, then I would need 2 hydrogens to balance it out. Or if my ion had a charge of -3, then I would need 3 hydrogens to balance it out. So it kind of works like ionics do, even though I kind of almost consider it its own subcategory. I consider it to be a little bit different just because of the way it works. Okay, so there are some tricks to acids and like the endings that attach on. I always look first on an acid name if I have hydro at the front. Because if I have hydro at the front of the name, and the ending says ic, then that means I have a non-metal in there, okay? So it's just an element that's with it, okay? If I don't have hydro at the front, but I still have that ic ending, then that means I had an 8 polyion in my acid. And then finally, if I see an us ending to my acid, then that means I had an ite polyion. Now, there's a funny little trick to remember this, okay? Here's the little saying you can use. I ate something icky. I ate something icky. All night, I was nauseous. All night, I was nauseous. And that will help you remember what goes together. I used to just say to myself, ic is 8, ite is us all the time. Like I'd check for the hydro first, and once I see it wasn't that, I would say ic is 8, ite is us. And that would help me remember what endings went with what. So take your pick on how you want to remember that. Totally up to you. So on this one here, first thing I would do is I would go look if I have hydro at the front. And I'm like, oh, well, okay, there's no hydro at the front. So that means I must have a polyatomic ion in here. So I look at the ending and I'm like, ooh, ic ending. That means I had carbonate in here. And I know carbonate is CO3 -2. Have we figured out yet we still need to know our polyions? Oh yeah, buddy. Gotta know those polyions, right? So I need to put enough hydrogens with this to cancel out that -2 charge, which means my final formula for carbonic acid will be H2CO3. And then with acids, I usually put the AQ symbol because technically it's only an acid if it's been dissolved in water, if it is, an aqueous solution. If it's a gas, which is common for some of these acids. If they weren't dissolved in water, they would have been a gas at room conditions. We actually use kind of like ionic rules to name it, like you would name it hydrogen carbonate at that point. So kind of keep that in mind that it's really only an acid if you have the AQ at the end. Now on this next one here, I'm like, oh, whoa, hydro. I see that at the front. And so then I'm like, okay, cool. This must mean that this is just an element. By the way, I will warn you, some of these have hypo. Be careful because hypo is different than hydro. So keep that in mind. I'm looking for hydro to be an element. We'll see a hypo here in a little bit. Okay, so I know that this is just going to have fluorine in it. And I come over here to my periodic table and I see that fluorine is in that group 17, meaning it's -1. And so that means I must have one hydrogen with it to balance out. So this is going to be just HF and going to be aqueous. All right. The last one that's going in this direction is this guy here, hexane. Anytime you see these one-word names like this, and you see ane endings to it, that indicates that I have what is called an organic hydrocarbon, something that just has carbons and hydrogens in it. I'm going to tell you some kind of more famous ones. Methane, propane, octane, things that we consider to be fuels. That you burn, like you have, a propane tank if you have like some sort of gas grill, or octane rating when we go buy gasoline at a gas station. So we've seen some of those before, but you're kind of watching out for those one names. And these are always covalent. So I don't have to worry about charges, but I do have to worry about how many hydrogens are in these. So I kind of got to be careful of my counts. First off, the hex part of this, the first part of the name, tells us how many carbons we have. Now, I do want to give you a quick note about the number of carbons. Okay. The first 4 hydrocarbon prefixes are kind of special. Methane, meth, eth, propane, bute, methane, ethane, propane, butane. A way to remember that order, meth eats people's brains, is for 1, 2, 3, 4 carbons. Okay, so methane has 1 carbon, ethane has 2, propane has 3, butane has 4. By the way, if methane sounds familiar, that's because that's what comes out of the gas valves in our rooms, in our classrooms for our Bunsen burners. So every time you light a Bunsen burner, you are burning methane gas. However, beyond 4, it actually uses the same prefixes that you're familiar with for covalent naming. So like pent, hex, hept, oct, nona, deca. Like those are the same. It's those Greek number naming system, okay? But the first 4 are different than the other covalents are. So the meth, eth, prop, bute. So just kind of remember that. So that hex tells us that I have 6 carbons, okay? So then to decide how many hydrogens I need to check to see if I have cyclo at the front of this. And here's why. And I gave you kind of 2 examples on this other sheet here. Notice that both of these 2 examples have 4 carbons. So both of them have bute in the name, which means it has 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. Okay. If you remember anything about Lewis dot structures and bonding and all of that, if you remember, carbon likes to make 4 bonds, right? So what happens is they're all bonded to each other, but when I have just butane here, I end up with 2 hydrogens on each of these carbons, okay? But then I also end up with these 2 more on either end. So the number of carbons is then doubled and has 2 added to it for the number of hydrogens. So like, for example, on this one, when I don't have that cyclo, that means I have 6 carbons lined up, 2 hydrogens way on either end, and then hydrogens kind of scattered throughout, okay? So I'm going to double that number and add 2 to it. So 6 times 2 is 12, plus 2 more is 14. If it did have cyclo at the front, what happens is those two hydrogens off the end get kind of removed, and the carbons end up linking up in a ring in a cyclic pattern. And so that's why it gets the cyclo at the front of the name. So for cyclo, you notice the number of hydrogens is just double however many carbons that you had. Okay, so let's go the opposite direction now and talk about Roman numerals, which I know are everybody's favorites. So first one, AgNO3. I'm like, okay, well, Ag is a metal, that's silver. NO3 looks like a polyion. Anytime I see I have 3 elements, there's a good chance you have a polyion in there. If you only have 2 elements in your compound, obviously you probably don't have a polyion. So, being ionic, I name my metal. So I would name the silver. And then I need to decide if silver needs a Roman numeral. Well, remember, silver, zinc, and cadmium are those 3 transition metals that I didn't highlight. We know that silver is always +1. So I don't need a Roman numeral with it. I just leave it as is. And then I go name my polyion of nitrate. Now, polyions do not get the endings changed when we name them in a compound other than acids. So I just call it silver nitrate and I'm done. Yay! Okay, so now let's look at the next one. SB, that's antimony. That's one of those that is like a weird symbol name hookup, okay? So with antimony, I see that it is in that weird section that we highlighted. It's one of those that could be +3 or +5. So when I name it, I'm going to have to include a Roman numeral for its charge. And to figure out what that is, I'm going to need to use the chlorine to help me. Now, chlorine has a charge of -1. It's in group 17. And there are 3 of those in there. So if I have 3 of those -1 things, then the only charge that antimony could be here to balance it out would be a +3. So what that means is when I name this, I'm going to name my metal. I'm going to put a Roman numeral of 3, and then I'm going to name my nonmetal. Now, in ionic compounds, nonmetals get that "ide" ending. So I wouldn't just call this chlorine here, I would call it chloride. By the way, again, the reason why we put the Roman numeral there is because if I had just written antimony chloride, and I asked somebody, hey, go back and write the formula for that, they'd be like, so what charge do I use on antimony? You see what I mean? Like, you wouldn't know. So that's why that information has to be communicated. All right, next one we see has that dot with the number of waters, and I'm like, ooh, that means I'm going to have that hydrate part at the end, which once I see that, then that means I know this compound at the front was ionic. Not only that, but I can kind of see a polyion in there that I recognize. So first off, Mg, magnesium. It doesn't need a Roman numeral. It's in group 2, so it's always +2. So I would just name it. So again, I always double check and make sure, do I need a Roman numeral or not? Here I don't, because it's always +2. Then I see I have a polyion, and polyions just get named. I don't have to change the ending, so I'm going to call it sulfate, because that's the polyion that it is. And then I'm going to use a prefix with the word hydrate to indicate how many waters. 7 is hepta, and then I name hydrate. That's a long one, isn't it? A little off the chart there, but that's okay. It works. Okay, so keep in mind those hydrate names get really long. All right, this next one here, I'm like, okay, Se, selenium. And I go look at it, and I'm like, oh, wait a minute. That's on the right side of that zigzag. So that means that guy's a nonmetal. And then I have another nonmetal. So this is one that's covalent, meaning I don't have to worry about Roman numerals or anything like that. Now, with covalent naming, you would use prefixes with one exception. We do not use a prefix if the first element is mono. I'll give you a great example of that. CO2. We all know that's carbon dioxide. You've never heard it called monocarbon dioxide, have you? No, I didn't think so. I haven't either. That's because I don't use a prefix if the first element is mono. I would if the first element was something other than mono, like we saw earlier with the tetraphosphorus hexoxide, that one did have a prefix on the first one. But if it's just mono, we don't. So I'm just going to name that element selenium. So the first element, I just name it without changing the ending. But the second element, I put my prefix, so hexa, and then I name it with the "ide" ending. Remember, fluorine has the flu, so hexafluoride. I always joke, fluorine has the flu because I see people switch the O and the U all the time. All right, so now I see here some things that have H in the front. And I'll be honest, a lot of times these also have AQ at the end. So I'm going to go add that in. We'll pretend that they had them there. And so that would be a nice indication that, ooh, I probably have some sort of acid. So when I do those acids, I would first ask myself, okay, what do I have in there? Do I have a polyion or do I have just a nonmetal in there? Here I see I have a polyion, okay? Bromate is BrO3. Bromite is BrO2. So BrO is hypobromite. Polyion, right? Okay. So I need to change this "ite" ending. Well, ic is 8. Ite is us. So that means I want to take off that "ite" ending and put us. But this hypo stays. That is different than hydro. Hypo stays. So I'm going to have hypobromous acid. Okay. Next one, got that acid format again. And I'm like, ooh, wait a minute. This is just bromine. It's just the element. And if I have just the element, then I do that hydroic format. I heard one time a funny little way of remembering it. Hydro in your name means no O for the polyion, no O in your acid formula. So hydro is no O. It has no O, no oxygen in the compound. And so therefore, this would get named hydrobromic acid. Just like we know HCl is hydrochloric acid. All right, by the way, these both have only one hydrogen because both the polyion as well as the nonmetal had a charge of -1. All right, last but not least down here, we kind of already talked about this one. C6H12, first off, I see just carbons and hydrogens. I always watch out for those when I have those covalents. I would recognize this as being a nonmetal and a nonmetal, but I see it's just carbons and hydrogens. So that means I'm going to use those one name kind of organic format to it, okay? So first, look at the carbons. I'm like, okay, I know I'm going to have hex in here. And I'm going to have the ane ending. But then I want to decide whether or not I need cyclo at the front of it. So that's where I look at my hydrogen count. And I see that going from 6 to 12 is just double. It's not double plus 2 more. So what that means is that we need the cyclo at the front of that name. All right, there's your overall naming blitz. Hopefully some of those names and stuff look familiar. As you can see, it's going to be really important that you know your polyions. It's going to be really important that you know your elements. So make sure you are refamiliarizing yourself with those as we go through. If you have any questions, please feel free to email me. Bye, guys.